So the first one I'd like to discuss with you is called kernel space or null space of linear map. It's two identical terms or two synonyms, kernel space or simply kernel or null space of linear map, and that's it's a subspace which is attached to a linear map, and that's how we define it. So if I have two quadruples, if I have two quadruples, V and W, it's a typical setting. I can zoom in a little bit. Okay, that should do for now. If I have two quadruples, V and W, which are vector spaces, it's a typical setting. It's a setting where we introduce a linear map, and if I have a linear map between these two vector spaces, the null space or the kernel of the linear space, that's the two notations, kernel of a linear map T or the null space of the linear map T, it's a two identical notions, they're two different symbols for the same thing. Here's a definition. It is the collection of all those vectors in the domain. Remember, we call this piece domain of a linear map. This piece we call codomain of a linear map. So null space, it's the vectors from the domain which are vanished by the linear map T. Null space of the kernel. The main thing we should know about the null space or the kernel, this is the main thing which I framed as a lemma. Null space, which is the subset of my domain, it is a subspace in fact. It's the main thing we should remember about the kernels all the time of the linear maps. And here's the proof. It's a very simple proof. If you were confident with the application of the subspace theorem in the previous chapter, reconstructing the proof for this lemma for you should be a very nice exercise, but I'll prove it anyway. Proof by subspace theorem. If you remember, subspace theorem has three criteria which we have to test. And here's my testing for the subspace. I'm just wondering, what exactly are you doing? Subspaces? Okay. That's all right. It's a nice subspace anyway. So the first criteria says, we just make this observation. We know that for the linear map, it is true that the zero vector is taken to a zero vector. So in the position of this x, zero vector may and will appear, and that's why zero vector is an element of the null space. And that's how we check the first criterion of a subspace theorem. Second criterion of a subspace theorem, if I start with two vectors from the null space, that means, I just interpret what it means to be in a null space. Here's the interpretation. That means that the T of x returns zero vector and T of y returns zero vector together. That's what it means. Now from here, I do the conclusion that if I compute T of x plus y, if I want to test that the x plus y vector is part of the null space as well, I have to make sure that the T of x plus y is 0, and that's how I make it sure. First, I use the linearity. This is the identity, which is the linearity of my linear map. Then individually, this one and this one is a zero vector, and that's why the sum is also zero vector. And that is enough evidence that the sum belongs to the null space. This is a second criterion of a subspace theorem tested, positively tested. Now, the third criterion of that subspace theorem says this. If I start with the vector x in the null space, again, I interpret what that means. Here's the interpretation. T of x is a zero vector. Now, I need to test this for the scaled vector. So here's my test. If I apply my T to the scaled vector, that's again the place where I'm going to use the fact that T is a linear map, this assumption on T. I can take alpha out because T is a linear map, and that goes into this because T of x is simply zero vector, and that is zero vector. And that's why we also know that the lambda x is in the null space of T. all three criteria are checked, and that's why the null space is a subspace.